A square matrix A has eigenvalues and eigenvectors, and this relationship here holds. Remember, this is the basic definition of what an eigenvector and an eigenvalue are. What if your matrix isn't square? If your matrix isn't square, then you don't get a lot of benefits. You don't get eigenvalues and eigenvectors. But it turns out that regardless of what dimension your matrix is, whether it's rectangular and what size it is, there's something similar to eigenvalues and eigenvectors that we can find for any matrix. So we're going to take a linear transformation that goes from R2 to R3, and we are going to execute it by a matrix multiplication with the vector. And let's say the matrix that we're going to talk about is this one. Now, because we are going from R2 to R3, remember that we have to have two input columns, or our vector has to live in R2 as the input. Now, at the same time, the output space is in R3, so every answer that we produce has to have 3 entries. If we take a look at the columns of A, these two columns are linearly independent, and that means that the range of this transformation, the thing it produces for outputs, is essentially just the column space of A, and this is going to be a plane in R3. If I take my matrix, it's 3 by 2. If I talk about its transpose is essentially going to flip the rows and columns. The transpose is 2 by 3. And if I sit here and I define a new matrix, let's call this new matrix G, and we'll go A transpose A. So at this point, what you should see is that we are now going to have a brand new matrix when we multiply this through. This matrix is 2 by 3. This one is 3 by 2. So we are going to produce a new 2 by 2 matrix. This matrix, when you sit here and do the matrix multiplication, is 74, 32, 32, 26. Now, this matrix, if you observe here, it's a 2 by 2. These off-diagonal entries are the same. This matrix is symmetric. Is it a coincidence that we got a symmetric matrix? And the answer is absolutely no. If I take any matrix like this, I would like to check whether or not this matrix is equal to its transpose. So that means I would use matrix properties, and the transpose of a product is the product of transposes, but in opposite order. And so what this is going to produce is it's going to produce A transpose A again. So what we've just shown is that regardless of what matrix we start, anytime we build this particular product, it will always be symmetric. Now, because of this, G must have orthogonal eigenvectors, and it must have real eigenvalues. And at worst, they're going to be 0. So let's find the lambdas and the v's. So the first step in doing this process by hand is simply just to form this usual determinant, set it equal to 0. Now this is going to end up being a quadratic because we've got a 2 by 2 matrix. And if you sit here and do the work, this is going to end up getting you lambda squared minus 100 lambda plus 900. This can be factored. We've got lambda minus 90, lambda minus 10 is 0. So as expected, we have 2 eigenvalues. They're both real. So at this point, we're going to find the eigenvectors that go with them. So let's say if we start with lambda is 90, we need to solve G minus 90I into this mystery V is 0. So what this is going to give us is negative 16, 32, and 0, 32, negative 64, and 0, which you can row reduce into 1, negative 2, 0, 0, 0, 0. From this result, you should be able to see that V1 is 2V2, V2 is free. So that means the first eigenvector that goes with this eigenvalue is just going to be 2 and 1. And we'll call them W for now. In a moment, we will change things. So let's find the second eigenvector. At this point, when we plug in lambda is 10, we will get 64, 32, 32, and 16. If you row reduce this, you'll get 2, 1, 0, 0, 0, 0. At this point, I'm hoping you can see that the second eigenvector here is going to be a 2 and a negative 1. Because G is symmetric, you should verify that if I were to take these two eigenvectors and take their dot product, I get 0. They are supposed to be orthogonal. We have found an orthogonal diagonalization for G. And what that means is that we are going to have some matrix here that works like this. Now, you have to remember that this should be an orthogonal matrix. That means it has to be square with orthonormal columns. And that means we need to normalize our two eigenvectors. So we're going to say that V1 is W1 over its length, which is then just going to be 1 over root 5, 2 and 1. And then V2 is also going to be 1 over root 5, negative 1 and 2. And this basis is what we need. So what's happened here is now we have found an orthonormal basis for R2, the input space. And that orthonormal basis is just these two vectors, 1 over root 5, 2 and 1, 1 over root 5, negative 1 and 2. And the orthogonal diagonalization is this matrix V, D, V transpose. This matrix V, it holds these two orthonormal eigenvectors, V1 and V2, so this vector here and this vector here. The matrix D is a diagonal matrix that holds the eigenvalues that corresponds to these things. So we'll have a 90, a 0, a 0, and a 10. By forming that special product A transpose A, we found an orthonormal basis for the input space. But you might say, well, I could have just found any orthonormal basis for the input space in any other way. Why did I have to do this? This matrix gives us something very special here. We are going to, on a whim, we're going to compute the following. We're going to take A, our original matrix A, and now we're going to multiply it by this vector here, 2, 1. So when I do that, I will get a 1 over root 5 coming out front, a 15, a 0, and another 15. If I take the second eigenvector and do the same kind of matrix vector product, I'll get a 1 over root 5 and a negative 1 and 2. If I sit there and compute this, what's going to end up happening is I'll get a negative 5, a 0, and then a positive 5. So what? If I were to take the first vector that I got and take its dot product with the second vector that I got, here's what ends up happening. I'll have a 1 over root 5 squared. So I'll get a negative 75 plus 0 plus 75. That's 0. The images of V1 and V2 in the column space of this matrix are also orthogonal. That's pretty amazing. And you might say, well, I don't get that. I found this special matrix A transpose A. I found that it was symmetric, so that means it has orthogonal eigenvectors. I took each of those eigenvectors and then I multiplied it by the matrix A. And it turns out those two answers, those two vectors were orthogonal as well. And I might say again, hey, is this a coincidence? So let's assume that for any matrix G that I build this way, A transpose A, let's assume it has orthonormal eigenvectors. like this. We'll say V1 all the way down to whatever, VP. If I take any two of them, AVI, dotted with AVJ, remember that I can write a dot product as a transpose. So this would be AVI transpose AVJ. And as before, the transpose of a product is the product of transposes in reverse order. And when I have matrix multiplication like this, I'm not allowed to change the order, but I can insert brackets wherever I'd like. And so I'm going to do this. And if you take a look at this, this is just our matrix G. And here's where the magic kicks in. I had to have picked those special eigenvectors of G, because now if you take a look at this part, this right here, this is just the eigenvector definition. So this is going to produce eigenvalue lambda j times Vj. So at the end of the day, this is going to be Vi transpose times lambda j Vj. This is a scalar, so I get to pull it out front. So I'll get a lambda j Vi transpose Vj. And we're almost here. So what this means is that I will now have one eigenvector dotted with the other eigenvector. And this is 0 because they are orthonormal eigenvectors. So this is an amazing result. Not only are the input vectors orthogonal, their images are also orthogonal. So that means all of these AV1 all the way up to AVP will also be orthogonal in the output space. They'll be orthogonal in the column space of A because that's where they're being dumped into. Now you got to be sort of appreciative of this special result. This only works if we choose those eigenvectors of G. It won't work for any other orthonormal basis of the input space. So for example, if I were just to take the standard unit vectors, 7, 0, 5, 1, 0, 5, and then multiply it by 1, 0, I'm going to get just the first column. And if I were to take the matrix and multiply it by the other unit vector, I'll just get the second column. These two answers are not orthogonal. I have to pick those eigenvectors of G. If I don't, it won't give me this magical property. We now know that if I take those two vectors that I just got, I know that they are orthogonal, but I don't know what their length is. So what we're going to do is we're going to create an orthonormal basis for the output space in this case, which is the column space of A, which is that plane in R3. Vector U1 is going to be vector AV1 divided by its length. And then we're going to define U2 as AV2 over the length of that vector AV2. And we're going to say that sigma 1 is the length of AV1, and we're going to say that sigma 2 is the length of AV2. We're going to give these two values special names. We're going to call these singular values. Now, just as a little note, if I were to take the length of any one of those vectors and square it, that's like saying AVI dotted with itself. So we're going to play the transpose game again. We're going to go AVI transpose multiplied with AVI, and we will reverse the order as we've been doing this several times up to now. This part in the middle is going to turn out to be that special matrix G. And just like before, this term here is just the definition of our eigenvalue and eigenvector. And that's a scalar, so we can put it out front. So we'll have lambda I times essentially vi dotted with vi. And because this is an orthonormal basis for the input space, that's got to be 1. So what we have is that the length of this vector squared is the eigenvalue, or if we were to now say the length of that vector, I need to take the square root of this thing. And here's where normally you'd have to be careful, but we are lucky. Because this is the eigenvalue of a symmetric matrix, this is always greater than or equal to 0. Symmetric matrices always have real and non-negative eigenvalues. So this will always exist. These singular values turn out to be the square roots of that matrix G. And these things will also always be greater than or equal to 0. In our case, remember that AV1 was the vector 1 over root 5, 15, 0, 15, which is like saying 15 over root 5, 1, 0, 1. And I can clean that up a little bit and make this 3 root 5, 1, 0, 1. AV2 was the vector 1 over root 5, negative 5, 0, 5. So if I were to take that out, I'll have a 5 over root 5, negative 1, 0, 1, which gives me a root 5, negative 1, 0, 1. If I'm going to define the first orthonormal output vector, I need to take AV1 and divide by its length, which I'm calling the singular value. Let's say that this is, or sigma 1, sorry, and sigma 1 is the length of AV1, is essentially just going to be 3 over root 5 squared, 1 squared, 0 squared, 1 squared. So this is going to end up giving me 3 root 5 times root 2, which is 3 root 10. And we're going to define this second singular vector, which is going to be AV2 over its length, or another way of putting it is AV2 over sigma 2, and sigma 2 is the length of that second vector, and that's going to be the square root of root 5 times negative 1 squared plus 0 squared plus 1 squared. So that's going to be root 10. So U1 was 1 over 3 root 10 times 3 root 5 into this vector 1, 0, 1, which is going to end up giving us 1 over root 2, 1, 0, 1. U2 is 1 over root 10 times the vector root 5, negative 1, 0, 1, which is going to be, once again, 1 over root 2, negative 1, 0, and 1. And that means U1 and U2 is an orthonormal basis for the column space of A, and that lives in R3, the outputs. If you take a look at it, we have AV1 is sigma 1 times U1, and AV2 is sigma 2 times U2. This was the result of those output vectors. So we're going to put this as a matrix equation. And when I put this as a matrix equation, I'm going to say the first equation is the first component, the second equation is the second component, and this is going to be sigma 1 U1, sigma 2 U2. So by definition of matrix-matrix product, this first term is the matrix A times V1 and V2. So this turns out to be an orthogonal matrix. And this matrix we're going to call capital V. So this expression here, we're going to come up with some notation. We're going to let capital sigma be this diagonal matrix that holds the singular values down the diagonal, and we're going to let this thing U star be the matrix that holds those orthonormal output vectors. Now note that this is not square. It's not an orthogonal matrix, but this one is square. This is a 2 by 2 matrix. We could write this as U1, U2 times the first column here, and then we could write it as U1, U2 times this second column. And that means this is U star sigma 1, 0, and U star 0 and sigma 2, which again, by definition of matrix-matrix product, is U star times sigma 1, 0, 0, sigma 2, which means this is U star sigma. So here's what we've got. AV is U star sigma. Because this is orthogonal, if I were to multiply by its inverse, which is just V transpose, and I do the same thing to both sides, I'm able to turn this into the identity, and here's what I will have. Any matrix A, the matrix A that I start with, can be rewritten in this way. Now, in our problem, A was a 3 by 2 matrix. This matrix U was also 3 by 2 because it held the two images of our input basis. This sigma was a 2 by 2 diagonal matrix, and this V transpose was a 2 by 2 orthogonal matrix. And this is what we are going to call the singular value decomposition of our matrix A. We are able to write it in this factored form that has something to do with input basis being orthonormal and output basis being orthonormal. And so the singular value decomposition of a matrix is a general result. It didn't matter if my matrix was rectangular or not. I was always able to do this.